Right, ladies and gentlemen, let's continue with the module in heat transfer, specifically convection. We are busy with internal forced convection. The convection part of the course consists out of 4 different chapters. Chapter 6 was on the fundamentals of convection. Then chapter 7 was external forced convection. Chapter 8 is internal forced convection, the chapter we're busy with now. And then after this, we are also going to do natural convection. So 4 different chapters. In terms of internal forced convection, it's most probably the most important part and the part that you as mechanical engineers are going to use most. Okay. And in this chapter, we already started with the differences, main difference between external forced convection and internal convection. Then we've started looking at the average velocities and temperatures. And then we also looked at the entrance region, how things developed with a boundary layer, with the velocities and the heat transfer coefficient. And at the end of the previous lecture, somebody mentioned to me that somewhere I've made a mistake here with the friction coefficient or the heat transfer coefficient with the writing of it, and that is so. I can't remember where, but as I think by now you know, there's quite a difference between what I mean and what I say and what I write. Okay, but I think by now you know how to handle that. Right, so let's continue with the entrance region, what happens there, and let's become a little bit more practical. Okay, before we are going to introduce very, very important concepts that I really want you to give lots of attention to. So by the way, if you have a blue pen and a red pen, please take them out. Maybe we're going to start using it now and with the next lecture, and I think even the lecture after that, and it will help you quite a lot. So if you have a blue pen and a red pen, it will help a little bit, just to make things clearer on your notes. Okay. So in terms of the entrance regions, there are a few, and there is a little bit of empirical experimentation that helped us to develop the equations that firstly for laminar flow, if the flow is laminar, then LH, okay, the distance, how long the boundary layer will take to fully develop. Okay, LH for laminar, okay, is approximately equal to 0.05 multiplied by the Reynolds number multiplied by the diameter. Okay, so that is how long it will take before the flow is fully developed with its velocity boundary layer. The next one is the thermal boundary layer. Okay, LT is for thermal, and again it is for laminar flow. Okay. Now that equation looks almost, well, exactly the same with one difference, and that is that we multiply by the Prandtl number. So D multiplied by the Prandtl number. Okay. So as you can see, it would mean that the thermal boundary layer would be equal to, not the boundary layer, the entrance region length would be equal to the length of the laminar one multiplied by the Prandtl number. Right. So it depends on the Prandtl number if it's larger than 1, smaller than 1, or approximately equal to 1. Okay. If it is smaller than 1, then it means the thermal boundary layer will develop first. If it is larger than 1, it means the velocity boundary layer would be fully developed first. If they're approximately the same, it would take the same length for both of them. Okay, right, so that's for laminar flow. For turbulent flow, it's very, very simple. Everything is 10 diameters. Okay, so LH for turbulent flow is equal to LT for turbulent flow, and it's approximately equal to 10 diameters. So very, very quickly with turbulent flow, the velocity boundary layer and the thermal boundary layer would be fully developed. Let's just do a few order of magnitude calculations just to give us a feeling for what it really means. Let's suppose the Reynolds number is 20. Okay, and the Prandtl number is equal to 10. Okay. And it is a tube. Okay, then the flow would be laminar. You agree? Because the Reynolds number is less than 2,300. Okay, it's a very, very very low mass flow rate. Reynolds number of 20, but the Prandtl number is very high. So it would mean that if we would then calculate LH for laminar, how long it will take before the flow is fully developed, then it would be equal to 0.05 multiplied by the Reynolds number, which is 20, multiplied by the diameter, and the result is equal to 1 diameter. Okay, the thermal one would then be equal to that one, 1d multiplied by the Prandtl number, which is 10. So it is 10 diameters before it would be fully developed. Okay, so schematically, that is our tube. Okay, and that is the diameter d. Okay. And this is now where your blue pen would help. If you use blue for the velocity boundary layer and red for the thermal boundary layer. So the velocity boundary layer would only take 1 diameter, then it would be fully developed. That is LH. Okay. Then it is fully developed, while the thermal one is going to take 10 diameters. So, like that. So that is LT, the thermal boundary layer. Okay. Right, now, when is the flow fully developed? The flow is fully developed when at 10 diameters. Okay. That is when the velocity boundary layer and the thermal boundary layer is fully developed. Okay. And it means the two boundary layers meet each other. Let's look at another example. We start increasing the Reynolds number a little bit. So let's increase the Reynolds number to just before transition. So the Reynolds number is 2000 just before transition, and the Prandtl number again is equal to 10. Okay. LH, laminar, would be equal to 0.05 multiplied by the Reynolds number, which is now 2000, multiplied by D. Okay. And that is equal to 100 diameters. Okay, so about 100 diameters. So if you use 2300 as typically transition, then you would know it's about 115 to 120 diameters before transition will occur. Okay. Right, so the thermal boundary layer would be the hydrodynamic one multiplied by the Prandtl number, which is equal to 10. So that is equal to 1000 diameters. Okay. So 100 diameters and 1000 diameters. So when we come back to this problem, we see in principle we have exactly the same. The hydrodynamic velocity distribution would be fully developed long before the thermal one, and the flow would be fully developed at 1000 diameters. Okay. Yep, next Tina.
I'm just curious, is there a particular reason why you're calling it the Reynolds number before transition?
The Reynolds number, yeah. The reason I call this the Reynolds number before transition is that what we're going to do in this course is the Reynolds number, the critical Reynolds number, where transition occurs is 2300 for a smooth tube like that. Okay, and that is what I'm busy with. So smooth tube, where normally transition would occur at 2,300. So for this case, with a Reynolds number of 2,000, it is just before transition. So the flow is still laminar. Okay. Right, so let's look at the case now where the Prandtl number is smaller than 1. So if the Reynolds number is equal to 20 and the Prandtl number is equal to 0.5, okay. I'm not going to write out everything now because it's elementary. Then we can calculate that LH for laminar flow is equal to, again, 1 diameter. Okay. And the thermal one would now be 1 diameter multiplied by the Prandtl number, which is now 0.5. So it is 0.5 diameters. So if we now look at this tube, and I'm going to increase the diameter a little bit to make it easier. If that is the diameter, D, okay, then it means it is going to take only 1 diameter before the two velocity boundary layers will meet each other, and the flow would be fully developed from a velocity profile point of view. But the thermal boundary layer is just going to take 0.5. So the thermal one is going to be there. Okay, so that is LT. Okay. And let's do it for the Reynolds number just before transition. About 2,000. Prandtl number equal to 0.5. Again, LH, which is equal to 0.05 multiplied by 2,000, is equal to 100 diameters. That is still the same. But now our thermal entrance length would be equal to 100 diameters multiplied by the Prandtl number, which is 0.5. That would be 50 diameters. Okay. So that is our tube. Okay. It would mean that LH would be 100 diameters and LT would be 50 diameters. So the thermal boundary layer would develop first, and in this case we will have fully developed flow at 100 diameters. And I think in this one I've missed putting it in, but it's very simple. We will have fully developed flow already at 1 diameter. Everybody happy with that? It's very simple, huh? Okay. Right, now, I've mentioned yesterday that if we look at the Nusselt number up to transition, then it is a little bit complicated in terms of how we do heating and cooling, and if the flow is only considered as forced convection and or mixed convection, where secondary flow occurs. So I'm going to start introducing it now. Normally what we do is when we look at laminar flow, specifically we have to distinguish between constant heat flux and constant wall temperature. So let's just discuss that again quickly because it's very important. Okay. So the two cases that we normally consider in heat transfer is the case of constant heat flux, okay, CHF, constant heat flux, just to save time, and the other case is going to be constant wall temperature. Okay, constant wall temperature. So those will be the two cases that we're going to consider. Okay, why are they so important? Well, for the following reason. Let's first look at the case of constant heat flux, where we're going to get that. Constant heat flux case will be where we will have a tube, and in most cases here we will refer to a tube, with a circular geometry, but the tube might have other types of geometries also. So in principle, what we're going to discuss will also be valid for other types of geometries. Okay, so the constant heat flux in practice we will typically get when we do heating with a current that typically would flow through a coil with a high resistance. Okay. So the electrical input would be equal to the current multiplied by the velocity, by the voltage drop. Okay. Okay, so we get this when we do electric heating. Okay. And then also in radiation types of applications, which would be in nuclear, okay, where the heat transfer is from radiation, and or with CSP systems, concentrated solar power. Okay, so where we use the sun to do the heating of a geometry. Obviously, it is a little bit more complicated to do that. I mean, if that is the sun, if you can just look at it schematically, and there's your tube, now you're going to get the radiation, but the radiation is not going to be constant all around the tube, except if you also use some mirrors on this side, so that you can also have reflections from all the different sides. So in general, however, these cases are always heating cases, almost never cooling. Okay, so heating cases, constant heat flux cases. Right, the other very important application is the constant wall temperature case. Constant wall temperature, as you can imagine, if that is the tube, would mean that the surface temperature is equal to constant everywhere. Okay, maybe I should have done it here, but in this case, sorry, if you can just maybe add a sketch here, just schematically, constant heat flux, as you can imagine, the heat transfer per meter or per square meter, whatever, stays constant. Okay. So schematically, that is typically how we're going to show it. The heat transfer rate. So every meter we will put in the same amount of heat transfer, or every square meter. That is a constant heat flux case. The constant wall temperature is the wall temperature remains constant everywhere. Okay, now normally that would be quite a very difficult thing to do, except for the fact that, I don't know, I think 90% of all heat exchangers in industry are actually constant wall temperature cases. How is that possible? Well, the secret is, you've already done it in thermodynamics, and that is to make use of the fact that there's latent heat in fluids. Okay. And when we have condensation or evaporation, the temperature remains constant, and a lot of heat can be removed or added. Okay. So on a TS diagram, if we just look at that quickly, think of thermodynamics. Typically the Rankine cycle. Okay. There's the pump. There's the, let me rather do it like that. Something like that. There's the expansion through the turbine, the pumps. Here we will have condensation. And here we will have evaporation. Okay. So the cycle direction would be typically like that. Okay. Okay. Now what is very important here is that condensation occurs at a constant temperature, except if there's a huge pressure drop. but then your design wasn't good. So you can prevent that actually. Okay. But relatively, that temperature can remain quite constant. On this side, exactly the same. That temperature during evaporation can remain constant. Okay. So it would mean that on the outside of this tube, we will have either condensation or evaporation. I'm going to show it just like that, just schematically. This is typically the gas phases, and in between we will have the fluids. Okay, so depending on what the quality is, there will be a mixture of gas and fluid. Yep.
I believe there's an error on the TS diagram. Isn't condensation supposed to be at the bottom?
No, actually, okay. I should have rather called that boiling. In this case. Yeah, okay, sorry. Boiling, yeah, sorry. Okay, boiling, condensation. Okay, I'm so used to the vapor compression system, which is now that one like that. Here we've got the compressor, and there we've got condensation, in this case, like that. And then through the expansion valve and the evaporator. Okay, there's the TE, and then there's condensation. Okay, so it depends on the direction of the cycle. The principle, however, is we have constant temperatures on the outside. That's very important. So if we have this tube, doesn't matter if it's now condensation or boiling or evaporation, is that on the outside we will have a mixture of gas and liquids. Now, you've already done it in terms of the resistance of heat transfer. So that would typically be the tube. I'm going to make it a little bit larger now. And the heat transfer will be determined by 3 resistance terms. Okay. The one here on the outside will be 1 divided by the heat transfer coefficient multiplied by the surface area. This one typically be the ln of the radii divided by 2 pi kl. Okay. That heat transfer coefficient is the heat transfer coefficient on the outside. This one is on the inside. So here we also have a 1 divided by the heat transfer coefficient multiplied by the area. Okay, so if we have either boiling or condensation or evaporation. Let's do it like this. The temperature, boiling, condensation, or evaporation, doesn't matter. Any one of them. Okay, so that would be that temperature. So if you think of this tube now, you can imagine that because we have this large part during which this temperature remains constant, we actually have something like that. And this temperature here is also either the temperature at boiling, condensation, or evaporation. So the temperature on the outside is quite constant all over the surface. You see that? Okay. Then the other thing is that this heat transfer coefficient, when we have boiling, condensation, or evaporation, is very, very large. So normally, heat transfer coefficients, when we have convection, not convection, sorry, natural convection, NC, natural convection. If we have natural convection, then a big heat transfer coefficient will be about 30 watts per square meter degree Celsius. Okay, that would be quite a big one for natural convection. Then for forced convection, that would be for something like water or air, a large one would go to about 1,000, or orders of magnitudes of 1,000. Okay. When we have either boiling or condensation or evaporation, then the heat transfer coefficients would be in the order of magnitude of about 3,000 to 100,000. Or hundreds of thousands, yeah, hundreds of thousands. Right, Tanya, so what would it mean? that value is very, very large, it would mean this resistance is negligible. Okay. This resistance is negligible, it would mean that this temperature on the outside of condensation, boiling or evaporation would be equal to the temperature on the wall. You see? So that is why this is such an important practical application of the case of a constant wall temperature. Any questions? All with me? Right. Okay. Now, we've seen that we've got developing flow, and apparently that's an important thing. Okay? And we look at the fact that we've got constant heat fluxes and constant wall temperatures, and we have the laminar flow regime, and we've got the turbulent flow regime. So let's start putting the picture together so that we can see what typically happens in practice for, firstly, laminar flow, and then for turbulent flow. And that would now be as a function of x. So any internal flow, typically through a tube, circular round tube, or a duct, square duct, or whatever, would typically have the following type of behavior. Let's first do the easy case, which is the case of turbulent flow. The case of turbulent flow, the heat transfer coefficient, okay, so that's heat transfer coefficient. Okay. The heat transfer coefficient would do something like that, okay, until it is fully developed. Okay. However, because it's turbulent flow, it only takes how many diameters? 10 diameters. Okay, so this thing should almost look something like that. 10 diameters, then it is fully developed. See that? Okay. Now we've looked at the two different cases of constant heat flux and the case of constant wall temperature. So the question is now, if we have these two different cases, what would the difference be? Okay. Now for the case of turbulent flow, if that is now the two cases, then it would look something like that. So the one case would typically be for constant heat flux, and the other one would be for constant wall temperature. Okay. So the difference between the two would be in the order of approximately 2%. Okay. So it is not important, that's the message. So if the flow is turbulent, it doesn't really matter what type of heating and or cooling method we do. Okay, so this line, let me just get another color, was now for a specific Reynolds number. So let's put in Reynolds number 4000. Okay, for 4000. If we do it at a higher Reynolds number, maybe 50,000, it would be exactly the same thing. It will just take 10 diameters before it is fully developed, something like that. And again, the differences would be so small that for all practical cases we neglect it. So if the flow is turbulent, we are not worried about the fact if it is a constant wall temperature or a constant heat flux. However, in the laminar flow regime, it is a big issue. Okay. So in the laminar flow regime, if we have typically the case of a constant heat flux, let me just say constant wall temperature is this one there. It takes a long time before it is fully developed, obviously depending on the Prandtl number and the Reynolds number, and the differences is very large. Okay. Now my sketch is not a very good sketch. Let me rather make it a little bit larger. Okay. So this is specifically for laminar flow. So for laminar flow, we will have LT, which is now that there. Okay. And then typically, from this point on, the heat transfer coefficient would be a constant. Okay, like that. Okay. So if it is fully developed, then the differences are in the order of about 20%. Okay. So this is for the constant wall temperature, and that the constant heat flux. You don't have to remember which one is on top or the bottom. So it's just the principles which is important now. Okay. While here, while it is developing, the differences are very, very large. Okay. So order of magnitudes, the differences here will be about 40%. Okay. While if it is fully developed, it would be about 20%. Okay, so that is why the heating method or methodology is very, very important when we work with laminar flow. Turbulent flow, it is not important, but even in laminar flow, we have to distinguish between the developing region against the fully developed region. Any questions before we proceed? Nothing? Okay. What we're going to do now is we are going to mathematically look at the case first of the constant heat flux, and then we're going to do the constant wall temperature. The constant heat flux case is maybe going to keep us busy for about an hour or an hour and a half. And then after that, I'm going to do the constant wall temperature, but I'm going to spend less time on it. But the principles, ladies and gentlemen, is very, very important. So it's going to be one of these cases where I'm going to do some mathematics, show things. And the formulas, yes, they are in the textbook, but with the application in the tests and the exams, this is going to be critical information that you really have an in-depth understanding, not of the mathematics, but the principles. Because it's really going to help you to solve some of the problems. And if you do not understand it, you're going to battle. Okay, so it's very important. Right. So let's start with the case of the constant heat flux. Okay, so QC is a constant. So schematically, as I've done previously, that is our tube. That temperature we're going to call Ti, the inlet temperature, and that temperature there is going to be Te, the outlet temperature. The heating is going to be a constant heat flux. So that is schematically why I show it like that, with all the arrows approximately the same length, to show that the heat every square meter or for every meter is the same. Okay. So Qs is equal to a constant. And the length is going to be L of the tube. Okay, so we know by now that the heat transfer rate can be written as the heat flux multiplied by the surface area over which we do the heating, which would be all around the perimeter. And that would be equal to the mass flow rate through the tube multiplied by Cp multiplied by, in this case, Te minus Ti. Because that temperature is going to be higher, we do heating. And the units is in watts. Okay? Okay. So, if we have the heat flux, it is 1 kilowatt per square meter, and we have the inlet temperature, which is 20. It is very simple to calculate the outlet temperature. Okay. So if we would like the outlet temperature, we can say it is equal to the inlet temperature plus the heat flux multiplied by the surface area divided by m dot multiplied by Cp. You all happy with that? Okay. So we can also write it as, obviously the area is equal to pi multiplied by the diameter. So I didn't put it in there, but let's use that as the diameter. I'm using a round tube, but it can be a square one where we change then the diameter to the hydraulic diameter. Okay. Okay, so it is equal to pi multiplied by the diameter multiplied by the length, which is the surface area, and pi multiplied by the diameter we call the perimeter P. Okay, P is the perimeter, pi multiplied by the diameter. Okay. Okay, so if we would put it in there, then we can write it as Ti plus the heat flux multiplied by P multiplied by L divided by m dot Cp, and let's call that equation 1. Okay. Right. This equation, we've calculated the outlet temperature. It's a very practical problem. In many cases, you know how much heat you want to put in, you know what is the inlet temperature and the mass flow rate, and you want to know what is the outlet temperature going to be. Okay, now what I'm going to do is, we are going to unfold this problem in terms of the calculation of all the temperatures of the fluid on the inside and the surface. Okay. And you can end up with one graph, okay, to save a lot of time. But what I'm going to do is I'm going to start with a graph, very simple, and every time I'm going to show it again, and then to show the new information, so that when you work through everything that you can understand conceptually what I was doing. Okay. So if we now would plot the temperature as a function of x, okay, and that is equal to x equal L. X equal L. Then what is known at this stage? What is known is the inlet temperature Ti, okay, and we can now solve the outlet temperature Te by using equation 1. You agree? So it is just very simply the transfer rate is equal to the mass flow multiplied by Cp multiplied by delta T. So nothing difficult about that. Okay. Now we would obviously like to know about what's the temperature going to be there, and there, and there, isn't it? And it is actually very simple to imagine. Because we have a constant heat flux, it means that every meter we put in the same amount of heat. So just intuitively, we would know that that temperature would increase linearly. Okay. But let's go and write down the equation or develop the equation. Okay. So we want to know what is the temperature. Take note of the fluid at other positions x. Okay, and that is very simple. We can take the equation that we've developed just now, the outlet temperature, which is equal to the inlet plus the heat flux multiplied by P multiplied by L divided by mass flow rate Cp. Okay. And we can just imagine that previously we had this tube of L, And this equation was developed for L. So for L, this equation was developed for L. So if we would make the tube half of the length, then the delta T would be exactly the same, isn't it? Okay. I mean, if we go and derive the equations now for the tube length of L divided by 2, all we need to do is put L divided by 2 in the equation. You agree? Okay. So in general, we can actually say that the temperature, and what we're going to do now is we're going to call it M, Tm. Okay. Tm, the mean temperature, as a function of x would be equal to the inlet temperature plus the heat flux multiplied by T multiplied by x divided by the mass flow rate divided by Cp. Okay. Now if this is the tube at length L and we are interested in the temperature, that temperature would be the mean temperature. Okay. Because remember, if we look at that schematically, we will actually have a temperature profile on the inside, something like that. Okay. Because at the walls, the temperature would be higher because there's heat transfer. And we've said that, you know, that's too much detail for us. We want to make it simpler. So we are interested in the mean temperature. So that represents the average or the mean temperature. So the mean temperature of the fluid can be written as that equation. Right. So let's go back to, again, our curve of temperature as a function of x. And that is equal to L. Okay. Previously we had Ti, the inlet temperature. We've solved the outlet temperature, Te. Okay. And what we can do now is we can solve the temperature everywhere inside the tube. And it's going to look like that. Okay. If we take a good look at that equation, we can actually see, if we just write it a little bit different, Tm as a function of x is equal to the heat flux, which is a constant, P divided by mass flow rate Cp, all of that a constant x plus Ti. Okay? Do you agree with me? So if we just rewrite this equation, you can see the heat flux we've set as a constant. The mass flow rate is obviously constant, otherwise we have unsteady flow. We don't want to make it that complicated. The perimeter is a constant. Cp is a constant, so, and that is the inlet temperature. So let's call this equation 2. So this temperature line is described by equation 2. Okay. And we call that Tm as a function of x. Now this line, if you can make it blue, because that is the fluid and the cooler side. Okay. So I know the colors most probably don't look that good, but that would be what is going to happen with the fluid temperature as we heat it. So it's a very, very simple case, constant heat flux, and that is typically what the temperature is going to do. The gradient of the line M is obviously equal to the heat flux, the constant heat flux multiplied by P divided by the mass flow rate and Cp. Okay. So the outlet temperature can be controlled. We can increase the outlet temperature significantly by doing what? Just putting in more heat, okay, you can see that, or decreasing the mass flow rate. It would give more time for heat transfer. Okay, obviously the P and the Cp are also two things that we can use to change the temperature in terms of inlet or outlet. Right, so That's very simple. The fluid temperature has been solved. The other case where we have the constant wall temperature, unfortunately, is not that simple. It's a nightmare. Okay. This one, very, very simple. Let's look at the surface temperature now. We would like to solve the surface temperature. Now with the surface temperature, what we do is, we shouldn't forget that we do not only have the equation of the heat transfer rate is equal to the mass flow rate multiplied by the Cp multiplied by delta T, but we can also say it is equal to the heat transfer coefficient multiplied by the area multiplied by Ts minus Tm. Okay, so Tm is the temperature of the fluid. Okay. And yeah, okay, let's rather do that. Indicate it is not a constant, because we can see how the temperature change. Okay, it's not a constant change. Okay. So we can write it in terms of heat flux, okay, is then equal to the heat transfer coefficient multiplied by the surface temperature minus Tm as a function of x. Okay. Now this surface temperature is also not going to be constant. It's also a function of x. Okay. So we can solve now from this equation the surface temperature as function of x is equal to the fluid temperature as a function of x plus the heat flux divided by the heat transfer coefficient. Equation 3. Right, I know about every day you get lots of equations. Okay. But what is very important is to look at this equation and to think about it a little bit. What does it say? What does it tell us? Okay. Has been given that, I'm almost finished, then we will finish. Okay. The first thing that is important is remember that is a constant. Because this is this category of problem. Okay, it is this category of problem. If we want to get the surface temperature, what do we need? We need this one, because that one was very easy to solve if a heat flux is given to us. If we can get the heat transfer coefficient, then this is known. That one we can solve at any position which we want, and then we can get the surface temperature. You agree? Okay. What is the problem? What is the problem? Remember, if I just come back to these cases here, we have a region of developing flow and fully developed. Okay. So, if the flow is fully developed, then the heat transfer coefficient is a constant. You see? Okay. So the heat transfer coefficient is a constant, very important if it is fully developed. Okay. And we will make use of that in the next lecture to solve the surface temperature in the fully developed flow regime. Thank you very much.